Welcome everybody, welcome back to another lecture on Introduction to Soft Matter. So till last class we had taken a container mechanics approach to this particular problem, and then at the end of that lecture I had said that today what we are going to do is we are going to take a very different approach to things. We know that no material is really a continuum, right? We know that matter is made up of small units called atoms and molecules, and the behavior of any material must necessarily depend upon how it is made at the small scale, right. So, there is a whole different way of looking at these soft materials altogether, and in doing so let us go back to a definition of soft materials that we had looked at in the beginning itself. So, the definition was that soft matter or soft condensed matter is a convenient term for materials that are in states of matter that are neither simple liquids nor crystalline solids. And in the same book, R.L. Jones, he says that in more precise terms the materials we are discussing include colloidal dispersions, where submicrometer particles of solid or liquid are dispersed in another liquid. So, this is the colloidal particle is one example of soft matter that he is talking about, colloidal dispersions, which is often in short just called colloids. And then we have another example in the form of polymer melts or solutions, in which size and connectivity of the molecules lead to striking new properties such as viscoelasticity, which are very different from those of a simple liquid. And then another example is liquid crystal, okay, where anisotropic molecular shape leads to states with a degree of ordering intermediate between a crystalline solid and a liquid. Okay. So, he takes three examples here. Colloidal dispersions, polymer melts or solutions, and finally liquid crystals. So, he is once again trying to give us examples of what are the different type of colloidal soft materials that are possible. Okay. So, basically soft matter includes a variety of materials, okay, and it includes a very large variety that is very difficult to fully enumerate. It includes a large variety of materials typically composed of polymers, colloids, liquid crystals, as the examples were provided, and other mesoscopic constituents. What does mesoscopic mean? What is this new word? Well, mesoscopic is a length scale that is larger than your microscopic length scale. Okay. And let us maybe discuss it with the example of colloid. So, remember in colloids we had said is a dispersion. So, colloids itself is a soft material, can be a soft material, or it can be an ingredient of another soft material. So, colloids themselves by a dispersion of one phase into another. And the other important thing to remember here is the size range that is specified. So, the size range is usually 10 nanometers to 100 micron. Some authors may say 1 nanometer. So, their size ranges might slightly differ, but that is not very critical. We are referring to a certain Let's write this clearly, 100 microns. So, we are referring to a set of length scales that are there, and these length scales see are much bigger than your atomic length scale, remember. So, when we say atoms, the length scale that should come to your first mind is approximately of the order of angstroms, but these are much bigger than that, right. So, it tells you that the material is made up of constituents which you cannot characterize by a length scale of simple, like a hydrogen atom of that length scale, you cannot characterize it by that. The length scales involved are much bigger. Okay. Now, since we are just discussing colloids, I just quickly want to point out that it can be dispersion of any phase, type of phase into any type of phase. Okay. So, I will just for completeness, I will name or give you some examples. So, this is the dispersed phase, and this is, let us say, the dispersion phase. This is the name. So, for example, you can have a solid body or solid particles that are dispersed in a gas phase, and then they are usually called aerosols. You can also have a liquid which is dispersed in a gas phase, and which case you would again call them aerosols. You can also have gas dispersed in a liquid, in which case they have a special name, foam. But usually we are considering some kind of solid which is dispersed in a liquid phase. Now, so it does not say that the definition you will note does not say what percentage. So, you can have the dispersed phase in any percentage you want, and if you have a very dilute solution, you can have a solution of, let us say, some solid particles in liquid, and then the liquid will behave more or less as the dispersion phase itself, right. So, the quantity of the dispersed phase is very small, let us say polystyrene particles in water, the percentage is, let us say 1 by 100th of even 1%, that is a very dilute solution, and the behavior of that overall liquid is going to be resemble more or less, the dynamical behavior is going to resemble more or less the behavior of water itself. But as you increase the solid percentage, you will start seeing that viscoelasticity becomes dominant at some stage, and for example, you have clay particles in water which becomes mud. So, as your amount of liquid becomes lesser and lesser and lesser, you have more and more viscoelasticity, apparent viscoelasticity that you see. So, in all these different examples, and we had discussed two more examples at least in that definition which was there, which is polymers and liquid crystals. We will look at those individually also. But the important point to note is that in soft materials, the operative length scale or the important length scale, what operative means, whatever is determining the properties of the matter, the operative length scale are length scale or scales are intermediates. Usually there are length scales, so intermediates between the atomic sizes and the macroscopic scales. Scales means length scales. So, you can have, let us say, a cheese ball which is 1 millimeter, and the atomic length scale here is going to be very small, obviously, as we discussed the atomic length scale. We will look into more detail about that in a bit. But the question is, what is the real operating length scale, or what is the length scale that is determining the properties of that material? That is somewhere between the large macroscopic length scale, where the thing becomes an object you can handle, and between the atomic scale. So, to understand this perspective, we actually have to look at the fact that matter is no longer can be considered as a continuum, as we had been doing in the previous lectures, and we have to necessarily adopt an atomic length, an atomic perspective to things. So, just like we have done in the past, let us look at a historical overview here. So, the fact that matter is made of atoms is actually a very old idea. Okay. It goes back to ancient Greeks and ancient Indians who realized this and wrote extensively on this topic, and many of the textbooks often cite the Greek ideas, and that is why the word atom comes from the Greek word atmos. And these ideas have been well cited previously. So, for example, in a paper of James Maxwell, and there is a reason I have chosen this paper, by the way, I will tell you in a moment. He says that the opinion that the observed properties, this is in the introduction section of this manuscript, and this is our great Maxwell, to whom the electromagnetic theories are credited to. He says that the opinion that the observed properties of visible bodies apparently at rest are due to the action of invisible molecules in rapid motion is to be found in Lucretius. In the exposition which he gives, the theories of Democritus as modified by Epicurus, he describes invisible atoms, and then he goes on to say that this is the ancient philosophy of the atomic structure of matter. And there is a reason I have picked out this paper, by the way. We will refer back to this manuscript when we are discussing the Maxwell's viscoelastic model. So, this idea is actually extremely old, that matter is made of these small constituents. And in the Indian system, the Indic philosophy, which is usually credited to this school, is credited to the philosopher Rishi and Rishi Kanad. He says that the Nyaya Vaisheshika, so this is from a different text, by the way, and there is a system of philosophy called the Nyaya Vaisheshika philosophy, and the Nyaya Vaisheshika philosopher has come to the conclusion that all sensible bodies are ultimately composed of extremely minute, invisible and infrasensible particles called atoms, Parmanu. Okay. And in this text, and I will tell you what text this is in a second, the author again states later on that according to him, and here this is a different portion of the text, this is I have taken it from a different part of the book, and he says there is a mathematician Raghunatha Siromani, who I believe was somewhere in the 14th century common era, and according to him the ultimate unit of matter is not an atom but a minimal gross body which has been called Thruti, the molecule of old philosophers. And here we see the word Thruti once again, and if you remember, we discussed this when we are discussing time scales, natural time scales. So, you see that in the Indic system same words are often used by other people, by different people for different meanings. So, we have to be careful, and this is taken from the book Studies in Nyaya Vaisheshika Metaphysics by S. Bhaduri. This is a very old text, 1947, and unfortunately the Vaisheshika philosophy, which is credited to Kanad, I believe Kanad goes to is before common era. So, some people say it is some 2nd century or 3rd century, although I am not exactly sure of the date right now, but this is an ancient school. Right, and it was even in the bhashyams of Shankaracharya, the Vaisheshika school has been referred to, and their idea of how matter is made of atoms. In this context, neither of the schools ever, to the best of my knowledge, ever made any conclusion or any guesses about how small the atom is. Right? What we are trying to do is to figure out how small the atom is. So, it is not just enough to say that matter is composed of atoms, then you have to figure out how small they are and how they are made of. So, these are ancient ideas, but in more recent history we have obviously the Brownian motion as an old phenomenon. I believe It was observed in 1820s, if I am not mistaken, by Robert Brown. It was also observed by other researchers, but Brown is credited to have done the most systematic study of Brownian motion, and that is why that phenomena is named after him. And in this, this again I have taken from a text. He concludes, Robert Brown, that the motion originated in particles themselves and called them active molecules. And this is from a book chapter in which I am one of the co-authors. The book chapter is titled Fundamentals of Diffusion in Microfluidic Systems. It is available in the Encyclopedia of Microfluidics and Nanofluidics, and I wrote part of this book chapter. And see, in the 1800s they have not seen how small they are, but people have started to make some conjectures about how small they are. And this is, I did not want to write so much, so I took a picture of this is a book I have. The book is called The Intermolecular and Surface Forces by Jacob Israelovich. Apologies to the author for mispronouncing the name. But this is a very interesting story where he says that at a meeting of the Royal Society of London in 1774, Benjamin Franklin reported on his interesting observation at the Clapham Pond, on which he had dropped a teaspoon of olive oil. As the oil spread on the water surface, it stilled the waves, a phenomena that was already known to ancient seafarers. Franklin noticed that this smoothing effect extended a quarter of an acre and no more. It is remarkable that neither he nor anyone in his illustrious audience thought of dividing the volume by the area to get a dimension, and it says 1 nanometer, for the size of the surface layer and hence of the molecules. This division was done later by Lord Rayleigh, but not until 1890s, more than 100 years later. And interestingly, one more estimate of the molecular size is attributed to Young, and it was probably around 1815 or something around that time. And he also got a value of 1 Armstrong, if I am not mistaken, for the atomic size. Although he published it in a place where people did not look, and he was forgotten, and it was only later on found that he had done this. Our understanding of the atoms obviously comes much later, proper understanding, although obviously there are a lot of scientists who have who even before the molecule is seen, and seen is in quotes, if I may use that, they have started using the idea of the molecular nature of matter, including Boltzmann and others. But only in the later part of the 1900s do we really understand how small the atom is with the Bohr model, right. So, you saw that how this idea of the atoms has developed, and in 1900s we start to have a very good idea of how the atom looks like, and the Bohr radius. So, one often says that the hydrogen atom in its ground state is approximately of the order of a Bohr radius, which is somewhere around 0.5 Armstrong, right. So, the atomic length scale that we just discussed is in the order of Armstrongs. Okay. The exact number is not important, right. For us it is not. If it whenever it is, we will come to that. So, we are discussing atomic sizes, right. So, the atomic size is the order of Armstrongs, and we know that atoms come together through bonds, and through the bonds they form larger units called molecules. So, bonds are usually of, or atomic bonds are usually of two types. One is called the primary or the covalent bonds, and the other is secondary or van der Waals bonds. primary or covalent bonds, sorry, just a second, I think I've, wait a minute, sorry. It is primary or chemical bonds. And primary or chemical bonds can be of different types, including, probably the first thing that would should come to your mind is covalent bonds. Another type is ionic bonds. And still another type are metallic bonds. So, in the covalent bonds, so example, so I ran out of space there, so I am just going to use, so covalent bonds. So, the water molecule is composed of, what is the formula there? H2O, right. Here your oxygen atom, this is just a schematic of this, can be represented as the oxygen atom having two covalent bonds with the two hydrogen atoms, right. Usually covalent bonds are highly directional, and single covalent bonds also allow for rotational freedom. Single covalent bonds also allow for rotational freedom. Not so much the double and the triple bonds. And when we say it allows for rotational freedom, we understand that there has to, the opportunity for rotational freedom has to be there. So, it has to be in solution form. So, you can have crystals where even though there are single bonds, you not have any rotational freedom, or rotational movement is very much restricted. The other type of bond, as we saw, so covalent, and then the other was ionic, right. So, ionic bonds are also very interesting and important. For example, NaCl, right, and these are composed of two atoms, Na plus Cl minus, and they are arranged in a lattice type of structure, where the force by which this entire thing is held together is provided by electrostatic force, right. So, electrostatic force holds ions in place. And this force is basically given by the two charges, the Coulombic force, or the Coulombic potential energy is given by the charges divided by the radius between the two. The force is in the square. Force has r square, this is the potential energy. Metallic bonds, just one more second here. So, I deliberately took an example of water and NaCl. So, water is a simple molecule, and we can see that the size of the molecule itself is of the order of the atom itself, right? It's slightly larger than obviously an atom, but it is of that order. Now, NaCl dissolves in water, but let us remind ourselves it is not going to form a colloid, by the way. When you dissolve NaCl, Na plus and Cl minus go into the interstitial spaces, and it breaks up into Na plus and Cl minus ions, and the size of Na plus and Cl minus again are in the order of angstroms. So, So, those are smaller than the length scale, the colloidal length scale that we discussed, right. So, that is why that length scale is important. So, salt in water forms a solution and not a colloid. And then we have the metallic bonds, which are considered a variant of the covalent bond but the electrons are delocalized here. But electrons are delocalized. So, the bonds are not that directional. So, the directionality is much lesser than that of a covalent bond. But interestingly, the strength of a metallic bond is of the similar order as a covalent bond. Okay, that is why they are important. Okay. So, what we will do is we will stop here for today, and what we have started doing in this particular lecture is that we have started taking the atomic view of things. Okay. We are just getting started with it. So, that is why the first thing we wanted to discuss is the atomic length scale. So, I gave you a small historical perspective, and then we know that what the atomic length scales are of the order of Armstrongs, and that they are put together. Different materials will have this different atomic bonds holding the molecules together. So, we just got acquainted with the covalent, ionic and metallic bonds for this class, and the next class we will look at the van der Waals bonds also, and go on to discuss how these are going to help us create larger and larger units from singular atoms. Right. Okay. So, we are going to stop here for this class.